Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about how does the surface-to-surface radiation model work. So just to give you an overview of what I'm going to talk about today, I'm going to start by talking about when do I need to account for radiation in my CFD models. I'm then going to look at what are view factors and how are they calculated. Then I'm going to move on to look at the surface-to-surface radiation model specifically, and I'm going to finish off by talking a little bit about the radiosity vector, because that's something you may see mentioned in your CFD manual or in the user guide. So, to start off with some motivation for this talk, when do I need to account for radiation in my CFD model? Well, the short answer is you need to account for radiation when the temperature differences are large. And what do we mean by large temperature differences? Well, if your simulation is going to be around room temperature, for example, and the temperature differences are very small, say 5, 10, 15 degrees, then radiation is probably not going to be important, as the dominant heat transfer mechanisms are going to be conduction and convection. So you can fairly accurately neglect radiation in those models. And what happens if the temperature differences are much larger? So what if we have a temperature difference of 100 degrees, 200 degrees, or even more? Well, we may remember back from high school that the radiative heat flux, Q, is given by equation 1. So Q, the radiative heat flux, is given by the product of sigma, the Stefan-Boltzmann constant, the area of the surface, and the temperature to the fourth power. So what that really tells us is that radiative heat flux scales with the fourth power of temperature, or the fourth power of the temperature difference. So as temperature differences get large, all of a sudden radiative heat transfer becomes extremely dominant, and we do need to consider it in our simulations. And just a quick point before we move on here, the notation I'm going to use capital Q for the radiative heat flux given in watts, and I'm going to use lowercase q for the radiative heat flux per unit area, so given in equation 2, and that's watts per meter squared. So just take a note and remember that motivation and notation as we carry on through the slides. So another point to quickly address before we move on, conduction and convection are transport phenomena that usually occur through the fluid volume, whereas radiation is a surface phenomenon that occurs on the surface of the solid bodies that we're solving for. So if we have a complex domain, normally with the CFD framework, we construct a mesh throughout the fluid volume and use that to solve for the conductive and convective heat transfer. But with radiation is only occurring off the surface of our bodies, as we usually find that the medium, whether that be water, another fluid, or a gas, doesn't tend to participate in the radiative phenomena. So radiation is only occurring off the surface. And in our usual finite volume CFD framework, we don't have an easy way to directly account for radiation because we solve for all of the cell volumes throughout the fluid volume. And for this reason, we're going to have to use some type of special treatment to account for radiation and a special radiation model. And in today's talk, I'm going to talk to you specifically about the surface-to-surface radiation model, which is one of the most popular radiation models you can use. So just a quick reminder of how we normally solve and account for conduction and convection in our fluid volume. Well, if we consider a cell that's on the wall of a solid body, given in the figure below, we know that our cell centroid is a distance yp away from the wall, and our wall is at some fixed temperature, T sub W, and we know the temperature at the cell centroid, Tp, and we calculated that temperature by solving an energy conservation equation. And what we find is that the heat flux off the wall into the fluid volume is given by equation 3, and that says that the heat flux is given by the product of the density, specific heat capacity, and thermal diffusivity alpha, multiplied by the temperature difference, T sub W, minus the temperature at the cell centroid, Tp, divided by that distance from the wall. So what we're doing there is we're really using a form of Fourier's law with a linear temperature difference between that cell centroid and the wall. And in a previous video I went through how we account for the heat flux from the wall if our temperature profile is non-linear, if we perhaps have a turbulent temperature profile between the wall and the wall adjacent cell centroid, and there's a link to that video in the description below this one if you'd like to go back and have a recap for how we account for a non-linear profile. But to summarize, we normally just modify the thermal diffusivity alpha to account for the non-linear profile, and that's how we normally account for the conduction from the wall into the fluid. That's how we normally do it, and then we solve our energy conservation equation to get the temperature in the entire fluid domain. But what we're looking at today is what happens if we have radiation as well, and the short story is radiation is an additional heat flux from the surface of the wall into the volume. That's Q sub rad there, and we're going to be looking at the surface to surface radiation model, which we use to calculate that heat flux Q sub rad. And then once we've done that, we calculate the heat flux, put it into equation 3, and then we solve our energy equation for the temperature throughout the entire fluid volume, accounting for conduction and convection in the volume. And if you need a reminder or a recap video of how we do that, I've also linked another video for how we solve the energy conservation equation in the link in the description for this video. So you can always go back and have a look at that one if you need a recap. So today we're just going to focus on that radiative heat flux there. And there, again, that's just a recap. Today we're going to be focusing on our equation for the radiative heat flux, Q sub rad, and then we put that into the energy equation and use that to compute the temperature field in the volume. So, to start things off, we know that for a black body radiator, the radiative heat flux is given by equation 4, and that's Q is equal to the product of the Stefan-Boltzmann constant, the area of the surface, and the temperature to the 4th power. And just a reminder for you, of course, a black body is a perfect emitter of radiation. And for our CFD models, our surfaces are often not black bodies. They're made up of materials such as perhaps steels, aluminium, or other regular materials that we see, maybe paint. And for these surfaces, the bodies are called grey bodies. They're not perfect emitters of radiation. And how we account for grey body radiation is we multiply that black body radiation by an emissivity given by epsilon. And as you can see in equation 5, epsilon is somewhere between 0 and 1. And if epsilon is 1, then we have a black body. And for our grey bodies, epsilon is going to be somewhere between 0 and 1. And it's just worth pointing out here that for the surface-to-surface radiation model, we assume that epsilon doesn't depend on the wavelength. We assume it's a constant, and it's a property of the surface that we defined beforehand. So equation 5 is how we can quite easily account for the radiation given off by our hot surfaces. But what we also need to consider is what happens when radiation that's given off by that surface is then incident on another surface. So quite often in our CFD domain, we're going to have a variety of surfaces, and they're all going to be emitting radiation and have a radiation incident upon them. So what do we do to account for radiation that's incident on a surface? Well, if we look at the diagram you can see there on the slide, we're going to consider a single cell K, and that cell is going to have some radiation incident upon it, and we're going to say that incident radiation is given by 1, and then of all of that radiation that's incident on the surface, some fraction is going to be absorbed by the cell, that's alpha K. Some fraction will be transmitted and will pass through the cell boundary, and then some fraction will be reflected by the cell, and we give that the notation rho sub K. And it's also worth pointing out here that for the surface-to-surface radiation model, we assume that the incident radiation is diffuse, and that means it doesn't matter what angle that incident radiation hits the boundary cell face at. We treat the radiation all the same. And equation 6 there is basically an expression of conservation of energy. So of all the radiation that's incident on the cell, some fraction is absorbed, some fraction transmits through the cell, and some fraction is reflected. So the next assumption that we use in the surface-to-surface radiation model is that all of our surfaces in our domain are opaque, and that means that they don't allow any radiation to pass through the cell at all. So all of the radiation is either absorbed or reflected. None of it is allowed to pass through the cell. And what does that mean? That means that we take tau k to be 0 in equation 7. The next thing we do is we use Kirchhoff's law, which states that the absorbivity, alpha, is equal to the emissivity. And what that really tells us, of course, is that, if you remember back from physics, a black body, which is a perfect emitter of radiation, is also a perfect absorber of radiation. That's really what Kirchhoff's law is telling us. So alpha is equal to epsilon, and we substitute that into equation 7, and what that gives us is equation 8, which you can see there, which says that the fraction of radiation that's reflected by the cell is going to be equal to 1 minus the amount emitted by the cell. And what does that really mean? Of course, if we have our cell that's a perfect emitter, then it's also going to be a perfect absorber, so none of the radiation will be reflected at all. Whereas if we have the other case where our cell doesn't emit any radiation, then it will reflect all of the radiation that's incident upon it. And for all of the cases in between, we use equation 8 to get how much radiation is reflected by the cell. So now we've put together all of the simple tools that we need to come up with a radiation model for our entire domain. We thought about how much radiation is emitted, that's given by the black body radiation, and we've also thought about what happens to radiation when it's incident upon a cell. Is it absorbed or is it reflected? So now we can come up with a radiative energy balance for a boundary cell face. That's a cell on the face of a solid boundary in our domain. And if we can write a balance for one cell, we can repeat that balance for all of the cells in the mesh and use that to come up with an equation and a model which we can solve for the radiative energy. So now what we're going to do is, if we consider our boundary cell face K, we're going to use the subscript K to denote the cell that we're interested in. And if we think about the total radiation that's given out from the cell, so equation 9 tells us that the total radiative heat flux per unit area that's given off by the cell is going to be the sum of the radiation emitted by the cell due to its temperature and some fraction of the radiation that's incident on the cell that is reflected away from it. And of course the emission is given by epsilon times the Stefan-Boltzmann constant times the fourth power of the temperature of that cell, and then the reflected energy is given by the reflectivity multiplied by the radiation that's incident upon that cell. And that's our radiative heat balance for our cell. But before we can proceed any further, it's worth noting a few points. The first point is that we know what the temperature of that cell is. We know what TK is because we've solved that using the energy equation in a previous iteration of our CFD solution. We know what the temperature is, but at this point we don't know what the reflectivity of the cell is, that's rho K, and we also don't know how much radiation is incident on that cell yet. So we need to do a bit of work on equation 9 before we can put it into a form that we can solve for all the cells in the mesh, and that's what we're going to do here. The first thing we can do is we can substitute in that relation that we derived for the reflectivity of the cell, so rho is equal to 1 minus epsilon, and we can substitute that into our radiative heat balance, and that's going to give us equation 11. So now we have the total heat flux per unit area out of the cell is given by the emissive power plus 1 minus the emissivity times the radiative heat flux per unit area that's incident on the cell. So we're making progress now. We're about halfway through deriving a full radiative heat balance for our cell. And the one thing we have left to try and work out is that QK incident on the cell. We need to know how much radiation is incident on that cell, and the point to remember here is that the radiation that's incident on our cell K comes from all of the other cells in the mesh. So even though we're considering cell K by itself, to get the total radiation incident on the cell, we now need to work out how much radiative heat flux is coming from all of the other cells in the mesh. So all of the cells are going to be linked in some way, and that's what we're going to look at now. So the way we do this, linking the cells together in the mesh, is we need to consider a view factor. And you'll often see view factors talked about in your CFD manual and in help guides online. So what is a view factor? Usually we use the notation F with a subscript with two indices for subscripts. So here I'm going to use F with J and K as subscripts. And what the view factor F means is it's the fraction of radiative energy that's leaving boundary face J and then arriving at boundary face K. And it's very important to remember the order of the indices here. So FJK means the fraction of radiation leaving cell J that's then arriving at face K. So sometimes you may see the form given in equation 13 where there's an arrow going from J to K to remind you that the radiation here is leaving J and it's arriving at face K. And of course this is a fraction, so it's going to be somewhere between 0 and 1. And what I've got for you there in the diagram is to remind you that if we have cell J there at the top, which is another cell in the mesh we haven't considered, and then we've got cell K at the bottom, which is our cell that we're interested in. And the radiation that's given off cell J, some of it will go to cell K and some of it will go to other cells in the mesh. And FJK gives us the fraction of that radiation that's given off cell J that's then incident upon cell K. And that's what we want to know here. We want to know what the view factor is. So a few more points before moving on with the view factors. Of course, if we think of energy conservation, then of all that radiation that's given off cell J, some of it may go to cell 1, to cell 2, to cell 3, to cell K. The sum of all that radiation must be conserved. And that tells us that the sum of the view factors, or the sum of the fractions, must equal 1. So if we look at equation 14, then if we take FJK, that's the view factor of the radiation leaving cell J incident on cell K, if we sum over cell K, so that's summing over all the cells that radiation is incident upon, then the sum of the fractions must equal 1. And that's one of our view factor identities, and it's purely a reflection of conservation of energy. And that's useful identity or useful fraction is often used later on when you're manipulating view factors, as we'll see. But this is really where it comes from. Another small point with view factors to remember is that if a cell can't see another cell because radiative rays travel in straight lines, if the cell can't see another cell, then the view factor is 0. It's view, it can't see the other cell. And I've given you a small diagram there just to help illustrate this. Remember that the radiation can't pass through the cell, it doesn't transmit through the cell, so our cell J there can't see the other two cells that are on the boundary. So the view factor for these cells would be 0. And of course, remembering that still if we sum up all the view factors for cell J, they will still equal 1. So that radiation that's being emitted off cell J will have to reach some other cells somewhere, but it can't reach our two cells that are on the boundary there. So how do we calculate view factors? Well, it turns out that calculating view factors requires a fairly complicated integral, which you can see there in equation 15. And what it basically says is the view factor, FJK, again the fraction of radiation leaving cell J that's incident on cell K, is the integral over the area of cell J and the integral over the area of cell K of 2 cosine thetas over pi r squared times by the Kronecker delta there. And at first glance you might think, well, what does this integral really mean and where does it come from? It looks fairly complicated, but where does it come from? Well, the thetas there give the angle of the cell normals to a ray that passes between cell J and cell K. So in that diagram there, you can see that there's a ray of radiation leaving cell J that passes to cell K, and the unit normals of these cells make some angle, theta, to that ray. And of course, if the angle's 0, the radiation's passing directly to the cell, so the cosine theta is 0. Whereas if the cells are at 90 degrees to each other, that cosine is going to be equal to 0. And the integral and the pi r squared basically originate from, we're assuming that we place a row of point sources all the way along cell J, and each of these point sources moves out in a spherical direction, and that's where we get the pi r squared from. And we sum up over all these point sources over both areas, and that gives us the view factor. Now the Kronecker delta there, which you see, comes in, and that will be given a value of 1 if the cells can see each other, or a value of 0 if the cells can't see each other. And of course, the cells might not be able to see each other if there's another cell or another object in the way. And still, you can see from this view factor integral that it's fairly complicated to compute, particularly numerically. If you've got a lot of cells in the mesh, their orientations are very different, and you have to evaluate, can the cells see each other? That's going to be a fairly tricky thing to do numerically, and it's not something that I'm going to go into detail for here. However, there are lots of papers and lots of resources you can look at in the literature if you're interested in how that view factor is calculated. But for now, it's sufficient to say that the CFD solver and the CFD code will usually compute all of the view factors for you before you start your simulation. And of course, it's also worth pointing out that we have to evaluate the view factor for every cell in the mesh incident on every other cell in the mesh. So if we have 10,000 boundary cell faces, then we'd have to compute 10,000 squared view factors, which is a fairly intensive computation even for modern day computers. So view factors are fairly complicated to calculate, but you should have a fairly good idea now of what they are and what they do. So now what we want to do is move back to our radiative energy balance again and look at how we're going to carry on doing that now that we've got an idea of what the view factors are. So if we go back to equation 16 and remind ourselves, remember we're looking at the total radiative heat flux out of the cell, and that's given by that's epsilon sigma T to the 4, which is the radiative energy given off the cell due to its temperature, plus some fraction of the radiation that's incident on the cell that's reflected off the cell. And what radiation is incident upon the cell? Now if we look at equation 17, we can start off by saying the total radiative heat flux that's incident on the cell is given by the summation over now all of the other cells in the mesh. That's all of the cells J. So remember here, we're looking at cell K, that's the cell we're interested in, and all of the other cells in the mesh are going to be given by the subscript J. So this time we're summing over J, and what we do is we multiply by the amount of radiation given off those cells, that's QJ, multiplied by their view factor, FJK. So the fraction of radiation from all of the other cells J that's incident on cell K. And we sum over all of those cells, and that will give us the total radiation incident on our cell K, which is what we want. What we're going to do now is do a bit of simplification, and to do that we're going to split the radiative heat flux into the product of the cell area, that's A, and its radiative heat flux per unit area, that's lowercase q. And we've done that for both sides of the equation in equation 17. So what do we want to do now? We want to cancel out these areas, because if we remember back to our CFD solver, we introduced the areas later on. So in our radiative balance, we don't want to have any areas involved at all in solving and setting up our radiative equation. So if we start with equation 18, on the left hand side, again we have the area multiplied by the radiative heat flux per unit area, and then on the right hand side the summation of the radiation given off all of the other cells J in the mesh. And what we're going to do the simplification is use the reciprocity relationship, which is given in that boxed equation in equation 19. And if you're interested in deriving this relationship, you can get it from the view factor integral that we looked at earlier by multiplying it by the respective areas and changing the indices there, and you'll arrive at the reciprocity relationship there. But what it allows us to do is, because the view factor for cell j onto k, so fjk, multiplied by its area aj, is equivalent to the opposite view factor, that's the view factor from k to j, multiplied by its area, we can go to equation 18 there, and on the right hand side substitute the area sub j times by that view factor with the opposite area and view factor given there in equation 19. And when we do this, we see that we have ak on both sides of the equation, and they cancel out, and that gives us equation 20 there. So qk, that's the radiation incident on our cell that we want, is equal to the summation over j being all the other cells in the mesh, of the view factor swapped around from k to j multiplied by the radiation given off those cells. And this is fantastic. Now that we've got equation 20, we can substitute that back into our radiative balance and make some progress. And this is what will happen. In equation 21, we take that radiative heat flux per unit area on the right hand side, which is given the underbrace there, and we substitute in the summation over the view factors and the radiative heat flux out of those cells. And that gives us equation 22, which is our final radiative balance equation that we were looking for. And what equation 22 tells us is that the radiative heat flux given off cell K is going to be equal to the emissive power from that cell, so epsilon sigma times its temperature to the 4, plus the reflectivity of that cell multiplied by the summation of the radiative heat flux given off all of the other cells in the mesh. So all of the cells are now linked together in one equation, and the unknown that we have here is the radiative heat flux given off all of the cells in the mesh, and these are all linked together. So if you're a little bit more astute, you may notice now that what we've actually got here is we've got a matrix equation, and that's what I'm going to show you on the next slide. So in order for you to help see where this matrix equation comes from, if you take the summation that was on the right hand side there and bring it onto the left hand side, we can now see that on the left hand side we have, for our cell K, we've got the heat flux out of the cell, and then we've got minus the reflectivity times by the summation of the heat flux over all the other cells in the mesh, and then that gives us on our right hand side the temperature of our cell K to the 4th power. And in order to see that this is a matrix equation, we think that K is going to be the cell we're interested in, so that's the diagonal elements, and then the off diagonal elements are given by the radiative heat flux that's emitted by the other cells that's incident on our cell K. And that gives us the matrix equation, which you can see there in equation 24. We've got our matrix of coefficients on the left hand side, which are 1s on the diagonals, and then the product of the emissivity and the view factors given there on the left hand side, and then our unknowns, our unknown vector is a vector of heat fluxes given off our cells, which are unknown, and then on the right hand side we have our known emissive power, which is proportional to the temperature of that cell to the power 4. And in simplified matrix form you may see it written as you can see there in equation 25. K being the matrix of coefficients, J being the radiosity vector, that's our unknowns, our vector of heat fluxes, and the right hand side being the emissive power E. And before carrying on, it's worth noting that that matrix of coefficients K on the left hand side, we have all of that information. We know the emissivity of all of the surfaces in our mesh. We've also calculated the view factors before starting our CFD simulation. So this is why when you load up your CFD code and you turn on a radiation model, often the CFD solver will calculate all of the view factors for you then and there before you start the computation. And this is so that you can assemble that matrix of coefficients there on the left-hand side. And we also know what the right-hand side is, because we know what the temperature is of all of the surfaces in the mesh, and we got that from solving our energy conservation equation for conduction and convection in our previous iteration. So we know what that is. And what we do is we solve that matrix equation for our radiosity vector J, and that gives us our radiative heat flux, which we can then apply as a boundary condition for our conduction and convection CFD equation. Then we move to the next iteration, we calculate the temperature field, and we use that temperature field as a forcing term back on our radiosity equation there in equation 24, and we update and calculate the new radiative heat flux vectors. So what you can probably see here from looking at these equations is that the radiation equation is solved alongside the conduction and convection energy conservation equation that we normally solve in CFD. They're coupled, and they're solved during each iteration of our overall CFD solver. And just a reminder for you that after you've solved that radiation matrix equation to get the vector J, the radiosity vector, then each of those radiative heat fluxes given by the Qs is the radiation that's emitted off the surface of each of our cells in our mesh, and we apply that and couple that with our conduction and convection matrix equation using equation 28, which is the boundary condition that we apply on the surface of all of our cells. And the radiation is an additional heat flux off the surface there. So just a few points before we wrap up. It's worth noting that that radiosity equation is a dense matrix equation. So we have non-zero coefficients for all of the terms in the matrix. And that's because a single cell in the mesh, the radiation that's incident on that boundary cell comes from all of the other cells in the mesh. And this is different to when we solve for conduction and convection, because the conduction and convection only depends on the cells that neighbour that individual cell. So the CFD equations are sparse and easy to solve, whereas the radiosity equation is a dense matrix equation and is a lot more expensive to solve. It's worth noting as well that the view factor integral is expensive to compute and is quite challenging. And for this reason, you may see a variety of algorithms used by different CFD solvers to make view factors and the radiosity equation easier to solve. And one such example is a technique called clustering, which you can always go ahead and read more about if you're interested to see how CFD solvers do that. So just to wrap up here, if you're interested in a bit more further reading, a very useful textbook is the Fundamentals of Heat and Mass Transfer by Incropera, and I've put a link in the description to this video for where you can find an online PDF of that textbook if you don't have it yourself, and there's a very detailed chapter on radiation and radiation modelling which you can use and look in a bit more detail if you're interested. And there's also, of course, the CFD user guide for whichever CFD code you use, and of course the ANSYS Fluent user manual is very good and very useful for that, and it's section 13.3.7 is the section that you want if you want to look at that. And again, with that one, I've linked that in the description below for this video. And that just about wraps up the video. If you have any comments, questions or suggestions, as always, I'd love to hear from you in the comment section below, and I'll endeavour to get back to you as quick as I can with those. And in the meanwhile, if you want a recap on the energy conservation equation, the conduction and convection equation, I've got a link to the video that I've done on that in the description below, and also another video for thermal or temperature wall functions and how we account for non-linear temperature profiles at the wall, and that's also linked in the description below. Until next time, thank you very much for listening, and I look forward to hearing from you.